Hi everybody, in this video we are going to go over 3 topics regarding electrons. The first topic that we are going to go over is the photoelectric effect. So first of all, light comes in discrete packets called photons, and these photons are just particles, remember? A photon needs a minimum frequency known as the threshold frequency to cause electrons to be emitted from a material, which is typically metal. Since frequency and energy are directly proportional, you can think of the phenomenon as something like electrons need a minimum amount of energy from light to hop off the surface. So a photon needs to have a certain amount of energy or frequency in order to excite an electron and make it hop off the surface. Anything under the threshold frequency or under the minimum amount of energy required to excite an electron off the surface will not trigger this effect. So, in this image, the very first image, this photon is under the threshold frequency, and since frequency and energy are directly proportional, that means that this photon does not have enough energy. So if this photon hits a piece of metal such as this, it will not excite any electrons, so it fails. Now what if you have many photons that are all under the threshold frequency? Now although you have a lot of photons, meaning that you have a high intensity or high number of light particles hitting the surface, it still fails to excite electrons because the individual photons don't have enough energy by themselves to excite each electron, because remember, one photon excites one electron, and if the photon doesn't have enough energy, then it won't be able to excite electrons off its surface. So as a result, this fails as well. So this tells us that it doesn't matter how intense the light is, and the intensity of the light is the brightness of the light, or how luminous the light is, and it's measured in a SI unit called the candela, I think. And because as long as the photon has enough energy, it will cause the photoelectric effect. So in the last image, this one photon is above the threshold frequency, so once it hits the metal surface, it will excite an electron off the surface, and this goes to show that it doesn't matter how many you have, it's just that as long as the photon itself has a frequency above the threshold, then it will excite electrons off the surface of metals. So how is this related to our daily life? Well, solar panels are the things you put on roofs, and they absorb sunlight and they produce electricity from the sunlight. So when the sunlight hits the surface, and remember, sunlight is a type of electromagnetic energy, so sunlight contains photons, and these photons excite electrons in the solar panel, and this causes electricity to be produced. So that's how the photoelectric effect is related to our daily life. And now let's move on to our second topic. Our second topic will be regarding the photoelectron spectrum. This spectrum shows the number of electrons in an atom, as well as each of their binding energies. Now the binding energy is the same thing as ionization energy. It's just telling you how much energy it takes to remove an electron. So the higher the binding energy or ionization energy, the harder it is to remove the electron. So electrons that are located closest to the nucleus tend to have a high binding energy and a low principal energy level. So let's read this graph. So this graph says that on the y-axis we have relative number of electrons. And looking at this, I kind of noticed that this peak is like 1, 1, and then 3, 1, 3, and 1. So notice how this is in a 1 to 3 ratio. These peaks are relative to each other. And what I also noticed was that these peaks might correspond to orbitals. So for example, this peak might be 1s2, and this peak would be 2s2, which is the next highest energy level. And then you have 2p6, and that's the energy level after the 2s2 sublevel. And notice how 6 electrons is 3 times as many as 2 electrons. So I think you're getting the trend here. After 2p6, we know that from our electron staircase that the next highest energy electrons are located in the 3s sublevel, and then it becomes 3p6, and then 4s2. So notice how the 2s are the lower peaks, and the 6s are the higher peaks. And notice how they're 3 times as high as this. So as a result, I've labeled this graph and I said that this is 2, this is 4, and this is 6 electrons. And it makes perfect sense, since this photoelectron spectrum is describing an element in its ground state, so it has to do something with the electron configuration of the ground state, and it all matches up in this graph. So as you might notice, the lowest energy level electrons, such as the 1s2 electrons, take the most energy to remove, since they have the lowest energy, so they require the most energy to be removed. Meanwhile, something like a 4s2 electron has a very low binding energy, which means that it takes not that much energy to remove that electron, and as a result, you can conclude that the 4s2 electrons have really high energy levels, and therefore they are easier to remove since they start off with a higher energy in the first place, and they need less energy to be removed. So heights of peaks are relative, but they represent the number of electrons, and each peak represents a sublevel. So we talked about that, and let's try to figure out which element this is showing. So as you can see, this is an element, so keep a note of that. And in addition, remember, in an element, it's not an ion, it's an element or an atom. So therefore, the number of electrons equals the number of protons. So we can count the number of electrons. So 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, and plus 2 is 20. So we have 20 electrons, and since elements are just describing the type of atom, that means that we have an atom on our hand. So number of electrons equals the number of protons in an atom. So this element will have 20 protons. And which element is that? Well, on the periodic table, the element with an atomic number of 20 is calcium. So this photoelectron spectrum is showing calcium, which is an element. So let's move on to the next topic, and let's talk about radio wave functions. So I'm not really well versed in this since it's kind of complicated, but I know for sure that radio wave functions come from the shape of the orbital, and these radial wave functions describe the shape of the orbital. And how? Well, I don't really know, but I do know one thing. I know that radial wave functions allow us to identify the type of orbital we have. So let me show you how to do that. So for S sublevels, you typically see a super duper steep line that goes up, and then it suddenly just curves straight down. And usually sometimes you might not even see the super duper steep incline, depending on how they zoom in on the graph. But typically the signature feature of S sublevels is that they start off like with this curve shape nearly touching the y-axis. So notice how for the 2S sublevel, it also does that. It starts by kind of touching the y-axis and then curving down. And same goes for the 3S sublevel. You see that it touches the y-axis really closely and then it starts curving down. And let's take a look at the 2p orbitals, or just the p sublevels in general. For the p sublevels, you typically see it kind of like arching up and then peaking up and going down like that. And the same goes for the 3p sublevel. It goes up and down like a hill. Now, what about D sublevels? Well, for D sublevels, it kind of just like does a hill, but it's a lot wider than P sublevels. So that's how you identify D orbitals. Now, for F sublevels, well, I've never seen that ever, so I wouldn't worry about that. And I couldn't find it in any of the Google images that I found. So let's not worry about the F sublevel. Let's worry about the S, P, and D sublevel. Now, how can we tell how this curve behaves after it starts at the beginning? Because, for example, for the 1s and 2s sublevel, notice how the 1s doesn't intersect the x-axis while the 2s kind of intersects it once. So how can we tell the difference? Well, it's memorizing time, and let's talk about a few things. Radio nodes are where the graph intercepts the x-axis. Now, to find the number of radio nodes, you simply take the principal energy level n, you subtract it by L, which is the second quantum number, and you subtract it by 1. So, for example, for 1s, we know that n is 1, and L is 0, since s corresponds to 0, and minus 1, and then you get 0. So, according to this equation, the graph intercepts the x-axis 0 times for the 1s sublevel, and that's true. It never intersects, as you can see. It kind of just levels off and never touches the x-axis, so it's asymptotic to the x-axis. Now let's find a number of radio nodes for the 2s sublevel. So for the 2s sublevel, we have, well, it starts with 2, and then we subtract s, which is 0, minus 1, and we get that is 1 node for the 2s. So it intercepts the x-axis 1 time. And as you can see, that's true. For the s sublevel, for the 2s sublevel, it intercepts the x-axis once, and then it levels off at the bottom. So you can do this trick for all of them, and let's do it one more time. For the 3D, so for 3D, it's going to be 3 minus d, which is 2, minus 1 is 0. So for the 3D sublevel, it intercepts the x-axis 0 times, and that's true. Because if you look at the green pattern, you see that for the green graph, it kind of levels off before it touches the x-axis. So by using the first trick that I taught you, by, reading the graph at the beginning and seeing how it behaves, you could identify the type of sublevel it is. And by using radio nodes and by looking at the equation, you can find how many times it hits the x-axis, and that will help you kind of determine maybe the principal energy level. So for example, if I were given the 3p graph, which is right here, I know that it's a p orbital since it kind of makes a hill, but it's not too wide of a hill, so I could claim that it's a p orbital, but I don't know what the principal energy level is. So how do I do that? Well, let's see how many times it hits the x-axis. So it hits it once over there. We don't count this part. We only count the parts that are after 0. So over here, this hits it once. So we know that the number of radio nodes for 3p is 1. So we can write 1, and this is equal to the principal energy level n minus L, and for p, L is 1, and minus 1 is equal to 1. So doing the math, you get that n is equal to 3, and that establishes the purple curve over here as a 3p orbital. So notice how radial wave functions let us identify the orbital, as long as you know how to identify the sublevel, and from there you could look at the graph and you could count the number of nodes, and then from there you could, find the principal energy level. Or if you were given that it was a 3p sublevel, you would be able to draw it, since remember for p it starts like a hill, and since 3p has one radio node, it'll intersect once and then it'll level off at the bottom and never intersect again. So this graph looks similar to the graph I drew here, but it looks a little bit messier, but that's fine. So that's how you do radial wave functions. Now, let's talk about angular nodes. Angular nodes are the number of planes that separate one orbital. So notice how the angular nodes is equal to L, the second quantum number. For S, the number of angular nodes is 0. Since a sphere, you can't really separate a sphere into different parts, so there are no planes there. And let's see, for P equals 1, well, why does P orbitals have only one angular node? Well, notice here there's this gap, and that gap is where a plane could be put. And that's why the number of angular nodes for P orbitals is 1. Now let's take a look at why the number of angular nodes for D orbitals is 2. Well, if you look at all of these, you could separate all of these with two planes. So for this guy over here, we could separate it like this, and, well, let me just use lines instead. You could separate it along this plane that I'm drawing as a line, and you cut it in half, and you can also separate it along here. So that's two planes. For this, it's the same idea, two planes. For this, there's one plane there and one plane there. And for this, oh, that's a little bit harder. It's like here and here. For this, it's just here and here. So notice how for all the d orbitals, you could separate them using just two planes. And notice where I separate them is where, like, it kind of, like, pinches into, like, an area that's close to 0. So for this one, you see how that point is, like, really just, like, touching it, and you could just, like, slice it apart because it's just a point. It's kind of just converging toward a point, so you could, you know, kind of separate it there. And that's how angular nodes work. And let's move on to the next topic. What happens if we square the wave function? Well, squaring the wave function gives you very useful information. It gives you the probability density for electrons in a subshell or sublevel, such as 3s or some other sublevel or shell. It's the previous graph squared, so all the values are positive. So notice that since these are just the squares of the previous graphs, you don't really have to memorize them, since all you have to do is square a graph. And I know I make it sound like it's easy to square a graph, but I mean, it's pretty hard, honestly. So that's why if you ever want to square a graph, if you ever need to, just take out a graphing calculator and square the graph, given that you actually have the equation for the graph. And I won't go over that here since that topic is a little bit more complicated and I'm not very comfortable talking about that, but I am comfortable talking about what the square of the wave function can tell us. It tells us probability density. So how does that work? Well, probability density tells us the probability that we'll find an electron given a distance r from the nucleus. So for example, at this point, you're very likely to find an electron in a 1s orbital given this distance r, since, you know, the peak is highest at this point. And remember, the y-axis is psi squared, which tells us probability. So you could substitute psi squared as probability, and that will make it easier. So let's now visualize the square of the wave function. So here's my drawing of an 1s orbital, and let's try to look at this and see how the probability density function is related to that. So the curve tells us that right at the beginning, when you're super duper close to the nucleus, you have a low chance of finding the electron. So let's just put, you know, a few electrons here. But it tells you that as you get to a certain radius r from the nucleus, it says that the electrons are very likely to be there. So let's just put a lot of electrons in this area over here where you're most likely to find the electron. So notice how, let's just say that the distance from the middle to here is the r, and it's the r that has the highest probability of finding the electron. But once you get too far away, it drops down and you're less likely to find an electron once again. So as you go farther and farther away from the s orbital, notice how the electrons are getting more dispersed and less abundant. So this diagram isn't showing you the number of electrons there are, it's showing you the chance that the electron will be there based on, like, how many electrons there are. So the number of electrons tells you how likely it is to be there given at any instant. And as we can see, at this ring over here, where the r is here and where the probability is highest, the electrons are most likely to be found there, so that's why I drew the most dots over there. So, yeah, I mean, I don't have an actual picture, but that's one way to visualize the square of the wave function. And that's all for this video, and have a nice day.